This lesson will cover inverse functions. The learning goal is to determine the inverse of functions and investigate their properties, to graph an inverse function, to apply inverses in a problem. Their success criteria is you're able to find the inverse of a given function, you're able to graph the inverse of a function, and you're able to solve problems that require finding an inverse. So a function is a relation between two variables usually referred to as x and y, where we start with the x value, apply the rule, end up with a y value. The inverse of a function means to do the opposite. So we start with the y value, do the rules inverse, and end up with an x value. So what it means is, for instance, if we had the function y equals 2x plus 1, well, we start with x. That's independent. Whatever x is equal to is going to change the value of y. And the rules would be we'd multiply by 2 and add a 1. But instead, we do it in reverse for inverse functions. So the notation of the inverse, well, we have f of x for function. For inverse, it's f to the power of negative 1 of x. Now, you might remember x to the power of negative 1 is equal to 1 over x. That is not the case here. This is strictly notation. It is notation. It is not an operation. It is strictly notation. It's just saying, hey, this is inverse. The function in its inverse has the property that if f of a, so if you plug the value a into your equation and you get b, if you plug b into your inverse, it's going to give back a. It does the reverse. It tells you, well, if you had used this value, this is what you would have gotten. So given the equation of a function, we can algebraically determine its inverse. And this is achieved by switching the x and y values and then solving or isolating for y. So really what we're doing is we're changing the x to y, making it y to x. So let's start with number 1 here. F of x is 2x plus 3. I'll say do y equals, I want to use y here, and then f inverse of x, that's x equals 2y plus 3. I switch x and y. So I solve for y here. I'm going to do x minus 3, moving the x over, equals 2y, and then divide both sides by 2, and that gives me x minus 3 over 2 equals y. So this is the inverse of 2x plus 3. Now let's actually test that for a minute here. Let's say we did x equals 3. We plug that into here. So you plug x equals 3 here, we get 2 times 3 plus 3, and that gives us 9. Okay, let's plug 9 then into our inverse. So we get 9 minus 3 over 2. That gives us 6 over 2, and that gives us 3. And that's what we started with. So this is what an inverse does. It really kind of gives us the output, or it gives us our input given an output. It's the reverse. Okay, let's look at these other equations here. So it turns out there that the inverse of a linear function is another linear function. Let's check for this quadratic here. So f of x, in this case, or g of x, is 2 times x minus 3 squared plus 4. And f inverse of x, that is going to be the same thing. So y equals, this is going to be x equals 2 times y minus 3 squared plus 4. And let's solve for y. So I need to, again, undo all these operations here. I can't touch the bracket yet. I need to subtract 4 first. So it's x minus 4 equals 2 y minus 3 squared. I can now divide by 2 on both sides. Gives me x minus 4 over 2 equals y minus 3 to the power of 2. I had this exponent, that's a 2. How do I undo that? How do I get rid of that? Well, remember back in Pythagorean theorem, if I had something like 25 equals c squared, I would square root both sides. That's what I'm doing here. So I need to square root both sides. So the square root of x minus 4 over 2 is equal to y minus 3. And then the root of x minus 4 over 2 plus 3 is equal to y. So that shows us that the inverse of a quadratic function is the root function. So if we had a graph, for instance, and here is our root of x, the inverse would look something like this. This would be, sorry, that's x squared of x squared. This is root of x. And you'll notice they kind of have this interesting reflection here. Now, you might say, wait a minute, shouldn't my parabola be fully reflected like this? But then that would make this not a function anymore. So when you do inverses, you have to remember that the root is just going to be the positive version of our outcome here. Okay. Now let's take our last equation here, where we start with the root function, and we're instead going to turn this into a quadratic function. So f of x is 2 times the root of 1/2 x minus 3 plus 4. And that should be y equals. Here we have x equals 2 times the root of 1/2 x minus 3. I should not make this root so big because we need plus 4 outside here. Okay, we need to deal with this plus 4 and here we cannot, we can't have that there, so let's subtract it. So it's x minus 4 equals 2 root of 1/2 x minus 3, and we divide both sides by 2. So x minus 4 over 2 equals the root of 1/2 x minus 3. And then I have the roots. How do I get rid of this root? The same deal as I just kind of did before. Instead, the opposite of rooting the value is squaring it. So I square both sides. So x minus 4 over 2 squared is equal to 1/2 x minus 3. I'm running out of room here. And then I need to divide both sides by half, which is essentially multiplied by 2. So 2 times all of this, x minus 4 over 2 squared equals x minus 3. And then we're going to add 3 to both sides. So my final equation, let's do it over here, is y, whoa, the whole time I've been doing 2 x's. y, and y. Well, I did not catch it earlier. So y equals 2 times x minus 4 over 2 squared plus 3. And that is our inverse. Inverse functions, graphically, you'll see them as kind of a reflection. Algebraically, they're going to reverse the x and y values, and you need to solve or isolate for the y in both cases. If you plug in a value for x on the original function, you get a y. If I plug that y back into the that result into my inverse, is going to be the original x value I started with, as we saw earlier. So if we're given the graph of a function, we can graphically determine its inverse by reflecting a function over the line y equals x. That's where this switching happens. Is if I'll get to it in a minute. If you look at this graphically, you're going to see that the x and y values switch. They switch positions for the inverses. So that's why you can also just take the coordinates of a function and just flip them. So what we're going to do is we're going to draw the line y equals x. So here's y equals x. Let's use a different color here. Let's use the fancy color. As much as I can make a perfect line going through all of these points, we want it as good as we can. Our function needs to be reflected on this line. And remember, to reflect something on a line, you just take the same distance away from the line. So for instance, I have this point here is distance away to this point. You just kind of take this distance here and apply it on the other side. So that point would end up right here. The points are on a line remain in the same position. So we can keep that in mind. And since we have these points here, we can actually already kind of create the graph from this. So here's our function. And notice how I'm not reflecting anything over here. That's because that would make this not a function. So I don't want to do that. I know that the inverse of this quadratic function is a root function, so I need to be very much aware of that. Now, I was talking about how you can switch the x and y values here. Well, this coordinate here, this is 4, 6. And this coordinate here, this is 6, 4. So that's why you can, well, reflecting on y equals x works, you can also just take the coordinates and just switch their x and y values. And that's why here for these points, these don't change because these coordinates are the same values. So 3, 3 becomes 3, 3, and 2, 2 becomes 2, 2. And we call these invariant points. A point that does not change between a function and its inverse. Because essentially, if you have a point where x and y equal, or so it's based on the line y equals x, then it's going to be an invariant point with its inverse. So algebraically, you switch x and y, isolate and solve for y. Graphically, you reflect on the line y equals x, or you just take the coordinates or key coordinates and then reflect or kind of switch their x and y values.